Hey, today we're going to talk about electronegativity. So, electronegativity is when two atoms get in a bond, there is going to be, on some level, a sharing of electrons. Okay? Now, if that sharing of electrons is perfectly equal, then we have what's called a pure covalent bond. If they're shared but unequally, then you have what's called a polar covalent bond, because the atom that wants the electrons more is slightly negative because it spends more time with the electrons, and electrons are negative. And if the electrons are kind of pulled closer to that atom, and they're over there more often, then that atom becomes a little negative, and then the atom that doesn't want those electrons as much is a little positive. And then you get something, the third type of bond is ionic, okay? And in an ionic bond, one atom just doesn't even want the electrons. It's just like, bye. And so he's like, you can have it. And so it's actually, formed an ion. And if you lose an electron, if you remember, we form a positive ion. And if you gain an electron or more than one electron, you become negative ion. And, you can lose one electron, become a plus one, lose two, plus two, three, plus three. And that's really kind of what we deal with. And same way with the negative monatomics. Now, electronegativity, and this is the work of Linus Pauling, among others. But what makes it really cool is that if you know the electronegativity value of an element, you can sort of put that bond onto a continuum about whether or not it has a lot of ionic character, covalent character, or if it's just a pure covalent bond. Now, with regard to electronegativity, fluorine is the highest electronegativity element. It's right up there at the corner, okay? And the reason why is because it wants only one electron. It will do many, many things to pull that electron to itself because it's the smallest element that will fill up that full 8, okay, to get that noble gas configuration. And so that's why it has this high electronegativity, is because it is searching out electrons. In a bond, it pulls the electron to itself. Nothing makes fluorine happier than getting that electron. And that's why it has such a high electron affinity and a high electronegativity. And you'll notice that electron affinity and electronegativity kind of go hand in hand, and to the point where a lot of people kind of juxtapose them and confuse them. But if you need to review what electron affinity is, go back to the video on it. And then on the other end of electronegativity is francium. Francium has this huge, it's like big, atom. It's just way out there, and it has that one valence electron. It wants to lose that valence electron, because when francium loses one valence electron, it becomes very happy with its own noble gas configuration. But in addition, it has all these other electrons that are blocking that last one it wants to lose. So you've got a huge radius, a lot of shielding. That electron is gone. It is just gone. Francium is really, really, really commonly a positive one ion. Okay? And then most other elements, fall somewhere in between. The closer you are over to the left of the periodic table, that's going to be your metals. Closer over to the right is going to be your nonmetals. They're going to have higher electronegativities because they want to gain electrons. And then as you get in the middle, it's kind of the middle. And just remember that the noble gases don't really register much on electronegativity. Some of the larger ones have values because they can actually form compounds. But as I'm looking at the one I gave you, helium doesn't register in electronegativity because you're not going to find a compound with helium in it. Same way with neon and argon. Even to every once in a while, I've seen an example with argon, but argon just doesn't really form compounds. Okay, so I'll show you how this works, and if you could maybe be following along with your um, chart. It just says it's under electronegativity. I'm not sure exactly what page this is on, but anyway, it's the multicolor one. So I'm going to do this real quick. So NaCl, Na is a 0.93, Cl is 3.16. So 3.16 minus 0.93, that's 3. 11 minus 9 is 2. So when I take the electronegativity, the larger one, the chlorine, from the sodium, I just take the difference of the two. Don't add them together. You're going to get all ionic compounds all the time. But when I take the difference here, it's 3.16 minus 0.93. I get 2.23 as my answer. I look at this. Boom, boom. That's going to be an ionic compound, and that's what we would expect. Salt is an ionic compound. Now, when I take water, H2O, and I just do one H and an O, oxygen is 3.44. Hydrogen is 2.20, so that's 4 to 1.24. That's oxygen, that's hydrogen. And so that's going to fall in between 0.4 and 1.8, so that's going to be polar covalent. And so what we'd expect to see is these electrons are being shared, whereas here you have like a sodium is a +1, has lost the electron, chloride has gained an electron, and they're in that big lattice energy. But here the electrons are actually being shared, but they're just being shared unequally. And so you would draw that like this. And since oxygen has the higher electronegativity, it's going to be up here and a little negative there. And then the hydrogen, since it's getting the electrons pulled away from it, is the positive. And then if you just have O2 like we breathe, that's 3.44 minus 3.44, and that's 0. And that right there is a perfect covalent bond. Totally covalent. And that would look that. Wow, that was a long video. Hope you made it to the end.